Alrighty, welcome everyone to week 6 of our Davis, at least. It might be week 7 or week 6 of total school, but that's wild. And today we're gonna jump right in, normal format, finish up with some tidyr stuff and get into plotting, which is exciting. So I'm gonna start screen sharing. And are we on my R screen? Okay. Great. Then, all right, same rundown. We're gonna go through the homework from last week, but checking things out just yesterday, it looked like some of you were a little behind on that, which is totally fine. Last week was a wash for the whole world and we're mid-quarter. But so I'm just gonna run through the first 6 questions just kind of on my own so that we can just sort of get in the vibe of coding, remember what we did last week, and then we'll move right back where we picked off into joining. All right, so if you're following along, it's also kind of always good to start out to check and say, okay, am I in my, wait, is this? Yeah, this is, I was like, wait, is this the project I want to be in? You should be in your project, which would have your GitHub username in it, because we're going to assume that you have the working directory that we're all going to be accessing for our data. But I'm going to jump right into the homework question. So we were going over some of the filtering, mutating, summarizing functions that we learned last week. And what we first wanted you to do was to just read in the data and call it surveys using this read, although important first step, which came up, is that we talked last week about what a package is, and we talked about Tidyverse, but we might not have mentioned that even though I've installed Tidyverse and I've loaded it in times past, every time I reopen this script, I usually keep these at the top of my script, and so hopefully it's at the top of yours. But calling upon library Tidyverse at the start of every session and running it, because you will always need to load these or else the accompanying functions will not work.
Liza, can you zoom in on your screen?
Yep, I tried to get there. Is that one better? I'm already a few. Okay. All right, so we have loaded our Tidyverse library, and now I was trying to do read underscore CSV, but that was not a function yet until I had called upon Tidyverse. And I'm going to do my read underscore CSV, which is how we read in our tibbles as a form of a data frame. Inside my quotation marks, I can call upon data, and I want the portal data joined. All right, so we're pretty used to reading in surveys from our data folder. And question 2, kind of to get you going, was first to not subset rows, but subset weights between 30 and 60 was the first question really of how to manipulate this data. And so a reminder, things we learned in the previous weeks are that the filter function will usually subset by rows and select will usually subset by columns. So if we're trying to subset surveys with particular weights, which are particular rows, we can start with surveys. We then are using our pipe that we learned a couple weeks ago. And we're going to use this filter function to call upon certain rows. And what we want is we want weights that are either greater than 30 or are greater than 30 and weights that are less than 60. Right, and then I think it also asked to print the first 6 rows. So we can use the print function and specify we want n to equal 6. And what we get in our output here is, you can see the head of our weights. We have 40, 51, 44. So these all look within our range, and we have a shorter number of rows than the length of our surveys data. So pretty basic filtering used there. The next question was to create a new column for the maximum weight of species and sex combinations, and then sort. So you can sort of check them out, the mins and the maxes, or the highest and lowest of these. So this is combining a few things that we learned last week. And sometimes when we read these instructions, it's hard to know which one to do first. Like I think we specified create a maximum weight, but for this certain combination. And this will just kind of get some getting used to the order of operations through these pipes. But typically, if you're trying to create a certain combination, I would say that we are going to be using the group by function, because that sort of will help organize the remainder of the functions throughout. I think this was also supposed to be called biggest critters. So I will start with that. Biggest critters are surveys piped through. And because we're also going to be asking for a maximum, I'm going to use this filter function, which we used a lot last week, to remove some of the NAs. I want to get rid of the weights that are that are not NAs, so we're filtering out those NAs. And then I'm going to call upon this group by function because we've asked for the species and sex combination. So remember, this group by is, when paired with other things, will sort of help you organize these more succinct tables later down the pipe and organize them by whatever column names you put in the group by function. And we can do more than one. So we want to group by, I think, species ID and sex. So now these are two categories that we're looking for combinations of. And then we want to get the max weight. So last week, we learned about mutating, creating new columns for the whole data frame. And then we learned about summarize, which is sort of condensing and summarizing certain categories based on this group by function. So because we're looking for this more like concise compiled result, we're going to use the summarize function. Z or S, doesn't matter. And remember, I want to assign a new value that is max weight. And I'll use my equal assignment here to specify that I want max weight summarized as the maximum of weight. And one last pipe. And this was a new function that you might have, I think, was maybe hinted at in the assignment, but using a function called arrange will help sort whatever you put in here, with the default being default is ascending, which we'll see in a second. And then I'm going to make sure I just print this out to view. So walking through lots of those different steps. Remember, now we've categorized by species and sex. We've created a new column called max weight. And this arrange function, this last one that we did, arranged the weights in a default of ascending order. So it started with the smallest value, and up to 54 rows, we'll get to the maximum of these maximums eventually, which is sort of a strange way of saying it. You can also look at it in the other direction. If now we've saved this as biggest critters, we can use our arrange function again, and we can then specify another argument within this, which is, or really another function within this, which is, I want to go arrange in descending order by max weight, which will start you at your highest, up at 280 now. So we can kind of see the full range of our max weights of these combinations. Before I jump to 4, I'm sort of like moving through these at a clip. Does anyone have any questions they want to verbalize real quick?
Actually, yeah, I just saw Christine's note in the chat saying that you need to specify if the filter's not working. Is that similar to how we read the library in for Tidyverse? You read in Diplier?
It is not similar in that you're opening up a library. It's just if you're trying to make sure that R doesn't mix up which library it uses the filter function, then using the colon method is saying I want to use filter from the dplyr package.
Okay, thank you.
Yeah, I think it was, Christian talked a little bit about this last week, but that sometimes functions can be masked. So like Christine was saying, if a function isn't working, it might be because you've loaded another library that masks it. And so by calling upon the actual package that it's from, which in this case is dplyr, you write in the function or the package name, use 2 colons, and then write filter, and it will work. But this is just something to keep in the back of your head if you have, if say code isn't working for you, this would be a way to sort of trace back and see maybe why, and maybe it's being masked by another package.
My comment was founded on that for some reason, after I updated some version of R, even if I opened Tidyverse and nothing else was masking filter, I would get these really weird error messages for filtering. And it was just because somehow that's happening and I didn't know it. So it was like a relatively recent thing that I've been having trouble with.
Huh. But yeah, that's good to know, because sometimes updates will sort of shift around what masks what. And I'm curious, we can maybe talk more about that later. I struggle with select being masked by another package I use a lot. So it could be a version issue, it could be another package issue. So these are the problems that will drive you crazy. Cool. So question 4 was kind of a vague question trying to ask you, like, where are the NAs in this data, which is not something we've necessarily gone over before. We've talked about, you know, how do I remove the NAs as if they're quickly unimportant? But often when you're inspecting your data, you want to know, is there some sort of systematic problem? Like, is something more prone to NAs? And, you know, that might be important if your data starts being abnormal in that way. So it's a pretty open question, and there were a few different a lot of right ways to answer this. I'm just going to go over one as an example because it can be repeated in many iterations. But one way of doing this would be to isolate your NAs by a certain category and count them up to sort of see, are there certain categories that have more or less NAs? So one example we prompted was to, you know, go into your surveys data frame, and instead of filtering out the NAs, instead of using that exclamation point, let's actually keep them. So I want to say within surveys, I want to look at only the weights that are classified as NAs. And then while this would just give us, you know, the whole data frame of NAs, it's still hard for us to sort of systematically look through them. And so this is where we could sort of rely maybe on our group by function that we've learned, say, no, I want to look at this more systematically, maybe say by species ID. And so now you can get a sense of by species ID, where are these NAs, but you remember with group by, you usually have to use an additional function. So we recommended, for example, the tally function or the count function, which will sum up or count up all of the species IDs with NAs. So if we run that, we could see, and we didn't order this in any particular way, so we're not sure, but already jumping out to us is that some species seem to have a lot more NAs. So this N now is a count of NAs. And we could, you know, if you know your species pretty well, you could consider why that might be the case, if they escape more easily or other reasons why you can't weigh things. But this is a really good practice, and figuring out, investigating more with proportions, with ordering them around, with playing with all different kinds of group bys would be a way, one of the many ways that you could have answered this question. But more often than not, it's like question number 5, where we say, can we remove NAs? Which is, I'm just going to plug in here. It's something that we've been doing pretty often, and I already did earlier. So if we want to remove NAs and create an average weight column for this same species and sex combination that we worked with for the last few questions, we would do our filter. We would do what we did earlier and the opposite of what we just did in the previous question, and use our exclamation point to get rid of NAs. And remember that I've been doing this, but we always have to specify now a column. I think when we first taught you this function, it was in a vector, and so you didn't have to say a particular column. And I have seen a few people in homeworks trying to do this on a whole data frame, which doesn't necessarily work. So filtering out the NAs, and then with this same combination, so I'm going to want to be group buying species ID and sex. What is my question? Oh yeah, I want to create an average weight. So whereas we did summarize earlier to create this sort of compiled and compact data frame, here we just want to make a new column called average weight. And so remember, our mutate function is this new column, but keeping all of your rows previously, except for the ones that we've filtered out. And so with mutate, we want to create an average weight column. We can call it average weight equals and use the mean function Don't need any additional arguments there. And I think we also asked you to select only a few certain columns, which I did not list in here, but I think we wanted to say, and then look only at species ID, sex, weight, and average weight. So this select function is pulling out just the columns that we list. And yeah, I'm interested in this no zero here actually, but so now we've identified just our species ID, our sex, weight, and the average weight that has been calculated per group. And so something to notice is that because we did this group by, we get this repetition of the average weights across these different categories. But because we use mutate with group by, we still maintain all of the rows in our data frame and get this repetition. And last question real quick, 6, which we're skipping 7 for reasons I will address in a second. 6 is then, can we say which of these rows or which of these items are above the average weight? So you can create a new data frame, surveys average weight, and let's see. So I actually did not assign this to anything above, which I should have done in order to work with it more in the following question. So I'm going to assign it its name. And then question 6 really just asked you, or I'm going to rewrite that new data frame that we've created. We're going to take surveys average weight, and in order to figure out which one of these are above average, we're going to use our mutate function again, make yet another column called above average, and we're just going to say, really ask it for this logical vector of is weight greater than the column we made in the last iteration of average weight. And if we execute this, then now we have this logical vector of trues. Eventually, some of them would be falses. And that is sort of the quick version of the manipulation that we're reviewing. So any quick questions on that?
Yeah, I suppose I'm a little bit confused. I was approaching the 5th problem a little bit differently, just from the read, and I got stuck, so I didn't finish it. But I thought you wanted a summary of the average weight for the males and females of each species, and the readout that you got looks like you've got like way more than 2 entries for each of the species ID.
Let's see for each species. I might have even copied it wrong. And create an average weight column. So I think that I'm even double checking myself. Like, I don't know what the actual answer was provided to you. And I think the thing is, neither is really wrong. Like if you use the summarize function there instead of what I did. So for instance, if you, like I said, we maintain the number of rows, but if you used the summarize function, there would probably be an issue because the select function would not work. Yeah. So if you were just trying to isolate like the categories themselves and did something along these lines where then you had many fewer rows, but still male, female, the issue with using summarize is that you would then no longer be able to see this information in the remainder of your data frame. So while I totally get that, like the homework questions, especially when you're asking someone to manipulate data, is really hard to like read and know exactly what the end result is. So if you ended up summarizing, that's totally fine. But I think specifically the question said, like to add a column to the full surveys data frame. And because we wanted this column added to the full data frame, only mutate is going to kind of maintain the number of all of these rows. And that's why we get this long repeated result for what surveys average weight actually is, which is a little silly, but is helpful for later data manipulations you might want to do. And it's all about
Okay,
sort of
yeah, I think that makes sense to me. I think I just wasn't thinking about maintaining all of the rows that we had.
Yeah.
I have a quick question too for, I think it's number 6. why are you having to reassign surveys average weight when you already told R what surveys average weight is above?
You don't, well, so if I had not reassigned it and just run this,
Yeah.
then while this output on its own has this above, like the one that's in my console has above average as a column. I already reassigned this, so this is a bad example. But if I hadn't, the next time I tried to use surveys average weight, that column would not be in existence. So oftentimes, if we mutate or create a new, all the time, if we mutate a new column, it will only save to the data frame if we reassign the data frame.
I see.
And
Thank
that's
you.
yeah, that just takes practice. I often I don't want to say forget to assign an object, but sometimes I do something really great and then it doesn't stick because I forgot to assign it to something. And it's usually harmless. I mean, as long as your code's there, you're like, ooh, plug in an object with an assignment arrow. And then it becomes a larger project management question of like, do you assign every new object like surveys average weight 2, 3, 4, or do you keep overwriting it? And this starts to become a personal adventure of how many objects you want in your environment. Cool. All right. So that was the homework that refreshed a lot of the stuff from last week. Question 7, I didn't bother going into right now because I'm going to talk about now in that we didn't go over pivoting last week. And that is pretty important to tee up prepping for ggplot. So I'm going to jump back in with joins and pivoting and we'll go from there. So where we left off last week was reading in another, so if you're following along, can you put up a green sticky just to verify, yes, I am in my appropriate project, and so I can sort of see my data folder, because we're going to be reading in data again, and just want to make sure we're all in the same working directory. And I see loads of green stickies, nothing red. Okay. So we should all be pretty good to then read in the, what is it? The tail length data. And we need this because we're going over joining real quick again. So to read in this new data, because, so if you recall, I left off talking about joins, which is taking one data frame and combining it with another one, which is a pretty important thing and comes up often. And so getting just at least some brief familiarity with these join functions is helpful. So to read in the tail data frame, we are going to call it tail. We're going to assign it and read in read underscore CSV. Again, we're going into our data folder. I asked about your project. I think now we should be comfortable with that's because my working directory then allows me to look directly in my data folder that's in it and pull out this tail length data frame. So now I have a new object tail in my global environment. And last week we already sort of verified this is the same length as surveys. If you haven't read in surveys yet, I would recommend doing that because we're also going to be working with our surveys data frame. Nope. And so I will just redo that here with you. So now we have both of our data frames in here, except I got an error because I got way ahead of myself. So we've read in both data frames. They're both have the same number of observations, and we want to combine data frames with join functions. All right. And if you'll recall last week, I kind of mentioned that the syntax or the arguments of join functions usually are join function, and then you have like data frame 1, data frame 2, and then a by equals a column name that matches. Specific. So in this case, we've taken, if we take a look at our surveys data frame, or maybe we'll actually look at, remember the call names function will let us see our surveys column names. So it's a quick spit out of how many different columns we have and what they're called. We can use this same function to look at tail. And tail only has 2 columns. but the column that they overlap on is this record ID. So this is the column name that we think if we have these two different data frames, we want to merge them together. And we want to do this by this matching ID that they both have. So in most cases, what we are going to be using is the left join function. It's worth, I'll pull this into the frame right now. I usually will just Google literally join dplyr, and this I think is the first link in Google, really join dplyr, join two tuples together. And then you'll have this long list of join types. Some of them are a little confusing, but I usually will open and stare at these descriptions every once in a while. And I'll just go over kind of two or one of the most basic ones really to get you comfortable with them. So the first one that I'll think that we use the most is left join. And left and right in these cases is really referring to which data frame is the foundational data frame that I want to like maintain the integrity of and bind other things to. So all the left is in the left join is really saying that the data frame that you put first on the left of the argument is going to be your like foundational data frame. So you can start seeing, I'll do left, and left join will pop up as an option. And remember, so data frame 1 is one argument. And so in this case, I want surveys to be my like foundational rock here. Surveys data frame, then the tail data frame is going to be my second one. And I want to merge them by, remember we identified that record ID is this column that overlaps. So what you'll see is, and we can do the call names of surveys left join. You can see in the global environment over here, we have 14 variables, which is a good sign because it's more than either of those. So something has happened. And if you check out the column names, what you'll see is that tail length has now been added. And what the by argument does is that it's not just like kind of patched them right on, it's knitted it based on the record ID. This is pretty simple and sorry, I'm checking my spelling of foundational, which it's not liking, but this is pretty simple if you have data frames that are of the same length. But what happens if data frames are different lengths? This is really where joining starts to get a little tricky, and the left or right or other longer list of these things starts to matter a little more. So one way to sort of inspect this, we don't currently have data frames that match but are different lengths. So we can create kind of a subset of our data just to run through a quick example. So let's say I want to identify, create like a data frame that has only the NL species. So this is really just for an example. I would quickly use my filtering functions to say, I want to filter the species ID that equals this species. So we can take a look at it. So great, now I have a much shorter data frame. My NL data is only 1252 rows. So now it's of a different length, but I still have all the same columns that I have in the surveys data frame. So if, for instance, we wanted to combine the NL data with tail, these are different lengths, what will happen? This is where the left and the right kind of start becoming important. So if you do NL left join, so we're going to put, nope, that's not what I want to do. I want to use the left join function, and I'm going to put the NL data on the left and the tail data on the right, and I still am going to do by record ID because this is still something these both share. What you'll see, and we're going to look just in the global environment, is that the NL left join data has just as many rows as the NL data. So it maintained sort of the foundation, the integrity of the NL data because we left joined and NL was on the left side. But if we tried to do NL right join, And so we do the exact same order. So we keep NL data on the left, but we're asking it to right join. What do we think will happen? How many rows will this data frame have?
However many are in the tail data frame, maybe.
Let's see. So tail is our 34,000 long. And we can see, I mean, we can look in this. I'm just going to look in the global environment. Now the right join, and we can look over here. I guess we can use our n rows column for NL. R join is the length of the tails data frame. So it keeps the right length now that we've right joined. So like I said, there's a suite of join functions, but this, and you can, it depends on the order you put your data frames in, the columns you select to join by, but this is just a little blink to say when you're joining data frames, these are sort of the mode that you should go in to think about, okay, which one do I want to keep the integrity of, which rows do I care about, which columns do I care about, and use that as your sort of foundation for thinking about going about these join functions. Does anybody have any questions about these?
I have a quick question that maybe you don't have the answer to, but I'm confused. Like, if you can just switch the order of the input data sets, why do you need a right join and a left join?
I wonder this myself. So like if I had done, I don't even know. If you do left join, but then you just switch tail and NL data, why would you not just do that instead, right?
I have an answer for this because I unnecessarily used join for the homework, and so when it's spitting something out of a pipe, I used a right join because I couldn't just change the order.
So you're saying that like sometimes you can't change the order based on if you're already piping through, they're sort of like fixed as a certain order.
Yeah.
Yeah, I mean, that's one answer. I don't know if anyone else has any experience like that. Maybe because pipes fix some DFs in certain positions. Anyone have any thoughts on that? Otherwise, I personally don't know.
That makes sense.
Yeah, I mean, it's like there must be a reason. And that I think that sounds like the best answer for now. And if I ever come across an example of otherwise, I'll let you know. Cool. So yeah, a quick introduction to joins. I've gotten lost in joins for hours, so one day you could too. But next we're going to switch to kind of the last of our Tidyverse information, which will sort of segue into plotting, which is pivoting. So pivoting has sort of gone or can go by many names. I would say pivoting equals transposing data. And in, I guess, I don't even think it's base R, but I think it's in reshape patch. There are a lot of words that you'll come across for transposing data. And some of them will be pivoting. Sometimes you'll come across cast and melt functions. I think it's in reshape package. And dplyr, or I will say Tidyverse, used to call this gather and spread. So I even just flipped through the R. Davis website earlier and tried to make an update because the words gather and spread were there and they're no longer relevant really. But know that if whenever you're Googling this sort of stuff, these words will also come up. And so we're going to teach you one approach to transposing data. And words that also come up a lot are this idea of wide and long data. So wide data, I mean, these are relative terms, but you'll kind of know it when you see it. Wide data are usually there are more columns. So let's say you have columns for each category of something in your data. which just usually equates to more columns. This isn't always true based on the size of your data. I'm going to paste in something that realizing that we can't draw on a board. That's sort of a limitation, but I would say wide data might look something like this. So let's say this is from our surveys. We have some different species IDs, and let's say that these are weights, but the column isn't labeled weight. We just know that the numbers inside the species IDs are weights. And this might be how we like intuitively think about data, I think, as humans. But oftentimes and especially for plotting, prefers long data, right? Which is sort of like stacked categories into one column. Usually this is longer in the sense that there are more rows, but again, it sort of depends on the data that you have. But I'll paste in sort of this same example that we just saw, where it's long, meaning categories for columns. What that would look like it's wide, meaning categories for columns. And what that would look like if it was transposed would be something more like this. So this is all the same data, but instead I now have a column for species ID and a column named weight. So this is the same data presented in wide and in long format. So knowing and understanding what formats some of your variables of interest are in becomes really important, as we've sort of noticed. This is what like group by is sort of starting to do. We like to coalesce things, we like to spread them out. And so pivoting is a way of moving data in these two different directions. So first, we're going to play around with these two functions, which are usually known as pivot wider and pivot longer. And to do this, we're going to work with a slightly smaller data frame, just because our surveys data has a lot of rows, and it's maybe just a little easier to walk through an example with a more precise data frame. So first, so just like before, this is just sort of a toy example. I'm calling this surveys MZ. I can't really figure out why that is the title, but that's what it is on the R. Davis website. And so I'm going to stick with that name. If anyone can tell what it is about this data that makes it MZ, please let me know. So just for this example, let's say I want to get rid of the NAs in weight. And I want to kind of create this summary of our data like we've been doing. My ukulele just fell on the ground. I want to take a summary of the genus and by plot ID, let's say. And I want to summarize this information so that we're going to get the mean weight. Is that what I want? So we're pretty familiar with these from the homework, and we'll take a look at it. So what surveys MZ is now a 196 row data frame that has mean weights as a numeric variable, and we have plot ID and we have genus. So just looking at this data right now, does someone want to shout out, is this in long or wide format?
Long?
Yeah, I would call this long. I mean, even though it's like, it's not actually as long as the other data frame. What I think makes this long is that genus and the categories within genus are all in their own column. So instead of each genus getting their own column, they're sort of compacted into one. So we're going to play around with, let's say right now this data is long. Let's make it wide. Okay. All right, and to make it wide, the function that we're first going to play with, you can see that I was prompted here for either pivot longer. I don't know if that's special, but we're going to ignore that, or pivot wider. So these are our main pivot functions in dplyr. You can, of course, always query what these functions are. And if you scroll down and look at pivot wider in the help window, you'll see that there seems to be a lot of different arguments that I can put in here. And there are. a lot because you can get really fancy with this. But the arguments that we're going to focus on right now are going to be the names from and the values from. So main focus. Okay, and what these arguments are really asking, because just like with join, the pivot functions are ones that I open up instructions and stare at kind of at length before I know exactly what it is I want to call upon within the data that I'm working with. Real quick. Okay, so got a little bit lost my notes. Okay, so the names from column, what you want, or the names from argument, what you want to specify here is the column with the values or categories that you want to be the names of the columns in the wide form. And similarly, the values from argument is going to be the column, I guess this doesn't make as much sense, column with values that you want to fill the new columns. So again, writing this out is always a little confusing, but so for our example, we'll go ahead and just give it a try. So we'll call this surveys wide. And we are going to take our kind of compiled surveys MZ. We're going to use our pipe, and then we're going to go for our pivot wider function. And our first argument, like I said, there are many, but the two you really need are going to be names from. And in this case, because what we noted is that in long form, it's that genus is sort of our elongated column. That's the one we want to make wide, and we want each genus to be the new column name. So names from genus, and we want values from equals. And in this case, we had plot ID and mean weight. We're going to go say we want mean weight to be what fills each of the new columns that we're making. All right, and check it out. All right, cool. So whereas our surveys MZ, as we had seen, only had 3 columns, we've now transposed it so that we no longer have a weight column like we did before, but instead we have much fewer rows. We have 24 rows because in a sense, that's really only the number of plot IDs that we have. And now we have new columns, each with a genus name that now carry the value that was in the mean weight column. Questions here? Think of it as I start typing out the next step,
So
which is that we're going to.
Is the numbers that are down in your column genus?
Yes. So in a sense, like wide data is not great, or at least in these examples, because nowhere in this data are we actually identifying that these are mean weights, right? Like in theory, you would at least want to say the name of the genus underscore mean weight. And you could potentially rename these, but in this example, these aren't good column names because it's not actually telling you what the value is representing. But yeah, those are the numbers that got transposed, just turned under each genus. All right, but if we want to switch it back and transpose now, let's say you have switch it back, say you have a wide data frame and you want it to be longer, which is, I find, often the case. We're gonna go with our pivot longer function, pivoting data from wide to long. And just like with pivot wider, we sort of have these similar lists of arguments, but in this case, there are going to be 3 arguments that are most important. And those are going to be the columns argument, which is short for calls, which are column or columns. So this can be more than one. I'm pretty sure that you want to select and sort of stack on top of each other. Those are not the best words, but I don't know how else to say it. The next argument is do argument, which is a column that summarizes the labels, really, that will come from your old column headers. So what are all these old column headers and what do we want to call them? And the values to is a column title representing then what the values that are being switched are. New title name for values. These all sound kind of vague. I'm writing them out because I usually have to do this every time I think about my data. And it always makes sense to put it in context. So we're just going to say surveys long. But now we want to take our surveys wide data, so the surveys data that we just created, and we want to flip it back. And so we can go ahead and look into our pivot longer function. And in this case, so what we're saying is, what are the columns that we want to stack on top of each other is this first columns argument. And so columns equals, and we can do this in two ways, right? I want to take all of the names of each genus and stack them on top of each other. So if we look at our data frame, that means columns here until however many columns there are. So two ways to do this. You could say, I want all of these columns, and you could do that by using our concatenate function, and you can start with the first column name that you want. You can really tell that I'm avoiding pronouncing these genus names because this is clearly not a data set that I work with. All right, so let's say I want to go to start to finish, which would actually, I'm grabbing this from notes, otherwise you wouldn't know this, but I would concatenate all of these columns together into this argument is one way of going about it. So I want all of these columns, and then I want names to now, so what do all of these columns have in common? What are they representing? This is where I would turn them back into a column called genus, because that is what these names are actually representing. And then the values, so all of these numbers that have been transposed into each one of these columns, what are what the values to argument is going to be the name of the new column of what those values actually are, which we know is average weight, no, mean weight. Yep, average weight. I might have spelled that wrong.
It's because you're using an assignment arrow instead of a pipe between surveys wide and pivot longer, right?
Ooh.
Yep.
Oh, yep. Thank you. These are the typos that get lost on me. And then I'll spend a while digging, like staring at spelling, and not that I used an assignment arrow instead of a pipe. So it had no data frame to be calling off of. All right, great. Thanks, Julian. So surveys long. If we can now see that this has been retransposed so that we have our same columns that we started out with, plot ID, genus, and average weight. You'll notice that this data frame is a little longer because it squared it off by putting NAs in columns or cells that didn't have any value. And so when we retransposed it, it carried through some of those NAs. But more or less, this is going to be the same data frame. So that's data transposition. We're right at about break time, but I want to check in on questions, thoughts, why this is important before we take a break.
Why is there the assignments of like surveys wide and the original surveys MZ? Do those maintain, so you could run any of those commands and flip back and forth between how you read the data long or wide?
Do you mean are each of those objects saved?
Yes.
Yeah, so that is a benefit to naming objects along the way. All of these have been saved. So close. So you could sort of flip through and say, okay, great, now I have my wide data frame, I have my long data frame, and I have my original data frame. And yeah, depending on what you want to do, one. If you make them, store them as objects, they're then there for your disposal for later summaries or plotting or whatever it may be.
Thank you.
All right. I think it's time for a break. It's 3 o'clock. So we can convene at 3:10 and we'll jump into ggplot.
Okay, it looks like most of us are back and the recording has started, so I'll take that as my cue to begin. I'm not sharing my screen, so that would be a good place to start. Let's see here. Okay, I believe you should be seeing my RStudio screen. I'm getting a thumbs up there. I'm going to zoom in. That's pretty far. Can everybody see that clearly? Okay, I see at least one thumbs up. So if you have problems, just shout out and I can change the size or whatever. So this is the point in the course that I get very excited about because I love plotting data and looking at data. And the Tidyverse that we've been using provides a really, really convenient and consistent way of getting into visualizing data. So the first thing we need to do is start off with a data set. I'm using the script that Liza started with class, so you should be able to pick up right where we left off. The first thing we're going to do is retain only complete cases in our data set. So I am taking this portal data joined and filtering it for complete cases where there are no NA values in any of the cells. So when we are plotting, I think a lot of people's sort of mental basis for plotting data comes from Excel. And Excel does a lot of things automatically that we don't really think about, but a lot has to go on in the background for us to be able to actually express data in a meaningful way. So the first thing that we need is a data set. And that we have through our surveys complete. So let's just look at this really quick and we can get an idea of what's going on. We have our record IDs, some time information, plot, species, hindfoot length, weight, et cetera, et cetera, et cetera. And so if we want to draw a plot, we kind of need a arena to start in that has defined axes, and then we can start adding material to that blank slate. So you could kind of think of it like a circus comes to town, but without carnies and elephants, it's not a very exciting circus. So the first thing that we'll do is sort of generate our circus by using this ggplot function. And ggplot stands for grammar of graphics plotting. There's somebody wrote a textbook on this. Like there's a whole philosophy behind how we think about applying graphical sort of parameters to data, or how we apply data to graphical parameters. So when I type ggplot, and this lives in the ggplot2 package, which is automatically loaded by the Tidyverse. So when we ran library Tidyverse up at the top of the script, that has automatically brought in all the functions that we need to get started with this. And you'll see that the parameters that we need to define in the ggplot function include data, mapping, and then some other stuff too. So the first thing that we'll do is tell it what our data is going to be. And we will use the surveys complete data set for that. And if we just run this over here on the right, I now have just a gray background with nothing interesting going on. Sorry, I need to move my computer so I can see my monitor here. Okay, now, so in using this ggplot function, yeah, we've kind of provided a circus tent, but there's nothing in our arena yet. And to add material to our plot, we use what's called aesthetic mapping. And that sounds kind of strange, I'm sure, but I think with 10 minutes, you will start to see where we're going with this. So we've sort of generated a canvas or a circus or whatever you want to call it. And now we need to tell our exactly what we're actually interested in plotting. And this is where that aesthetic mapping comes in. So if anything that we are so-called mapping aesthetically is like a layer of paint on a canvas. And when we're using these mapping aesthetics, they are typically a variable that we already have measurements of, and we will apply some sort of measured effect in our plot that accounts or includes that variable. So let's add some variables to our plot. First, we need to kind of start over, because ggplot in and of itself, that's a line of code, but it didn't give us anything interesting. We can add a plus to the end of that line, though, and start a new line, and that points our to understanding that we have more than just that line of code, and it needs to interpret everything that comes after the plus at once with it. And so we could use some sort of geometry to add material to our plot. So if we wanted to generate a scatter plot, we would use the geom point function, which belongs to ggplot. And within this too, we will add stands for our aesthetic mapping. And you can see within AES, it's already recommending we have X and Y. And this is where we will define what our actual plotting parameters are going to be. So we could say AES X equals weight and Y equals hindfoot length. And let's see what happens. Hey, there we go. So you can see here now we have taken our little blank canvas that went along with our data set and added axes and placed points where each of those data live. And so this starts to look more like what you might expect from a plot. We can also feed some of these parameters directly to ggplot. So we can feed aesthetic mapping info to ggplot directly by, and I'm going to do a lot of copying and pasting here because I want to illustrate stuff and not spend a ton of time typing. But so directly within our ggplot parentheses, we could define our aesthetic mapping as well and say X equals weight, Y equals hindfoot length. And if we just run this by itself, you might notice that I didn't give ggplot any sort of get the axes that we expected, but there's nothing on the plot because there's no geometry that R understands it needs to add. So instead, we can use our plus sign again and say geom point. And suddenly this will give us the same material that we generated above. I want to take a quick pause because this is a lot all at once. Did everybody, let's do a little sticky check. If you were able to generate a plot that has a scatter of hindfoot length versus weight, go ahead and throw up a green sticky. And if you had trouble with that, put a red sticky up. Okay, it looks like everybody, I think. Are there 2 versions of Connor's account? All right, it looks like most of us have plots set up. If you have problems, go ahead and just type into the chat and we can work through that individually with you. Let's see. I need to move some windows around here again. Okay. So like I was saying, ggplot allows you to sort of paint and add iteratively. And you can sort of keep adding material to your data, to your plot, by using more and more pluses. So perhaps we're interested in the linear relationship between these different factors. And we could then add maybe like a statistical mapping that would be stat smooth, and that'll add a smooth line to our plot. Hopefully. Yeah, and that looks disgusting. And there's a reason for that. We have a ton of underlying variable groups within the data that have their own meaning. So it can be useful to tease apart some of this information. And I kind of got lost track on the course lesson plan, so I'm going to try to combine a couple things at once here. One thing that we might be interested in is group level variability. One thing that we might want to do is say, okay, well, there were a bunch of species in this data set. And so we could take the graph that we just made, but then add another aesthetic mapping and map our species to the color of the points. And we can do that within the geom point, or we could do that within the aesthetic mapping in the ggplot call itself. And both of these will give us the same answer because everything is sort of defined at once at the beginning. Now you might notice there's a lot of overlap between these points, and there's so many points that it's actually kind of hard still to see what's going on. So one thing that we might want to do is set some transparency to our data, and we can use that. We can do that with this so-called alpha parameter. And alpha basically is a scale between 0 and 1 that defines how opaque our geometry should be. So if we set alpha to 0.1, it's going to be a fairly transparent point. And now you can see where there are core groupings of points in the plot, it looks a lot more opaque because there's layering that's going on across the points. But where there's very few points, like this orange one that's at maybe 40 grams and 65 centimeters in hindfoot length, you can barely even see that because the transparency is set so high. So let's see, I think that might set us up well to start this first challenge. And I'm going to add that to the chat right now. So let's see, it's 3:24. Why don't you take 3 minutes to work on this challenge alone? And then we'll just reconvene immediately after that because there's a longer challenge that I want to try to do before the end of class. So take a couple minutes and try to apply what we just did, but rather than having weight on the x-axis, put species ID on the x-axis and weight on the y-axis. And then sort of think about what you're actually visualizing there and ask yourself if there's a better way to graphically display those data. Okay, it's been about 2.5 or 3 minutes. Did anyone come up with a solution for getting weight and species ID plotted together?
Yeah, I basically just, to be honest, copied what you did just above and put X equals species ID, Y equals weight.
Okay, so you have data equals surveys complete. And then did you put the aesthetic mapping in the ggplot or in the g-on-point?
I put it in the ggplot.
Okay, so you have X equals, what was it?
Species ID.
Species ID. And Y equals weight?
Yeah.
And did you color code by plot type?
I did. I color coded by species ID. Oops.
Okay, so
I
did you
forgot to change
have,
that.
I'm sorry?
I forgot to change it to plot type.
So if you had color equals species ID, did all of your columns have unique colors?
Yeah, they did. Yeah, that's what it looked like.
Okay. And did anybody do that but with plot ID? And it looks like for plot ID, we have kind of a disgusting mess of colors interspersed within species ID. This is really hard to look at, isn't it? Does anybody have an idea for how we could better visualize this?
I have a quick idea. I mean, it kind of looks like what you're interested in looking at with this graph is the variation in weight by species and then by plot as well. So is it possible to have just a graph that has a single point for the average weight of each plot ID?
That's a great idea. You might lose a little bit of information about the spread of the data if you start to apply mean willy-nilly. But that would be a great start at making this something that would be more meaningful and readable. Did anybody else have ideas?
I tried viewing it as a box plot rather than a scatter plot, but it still looks really messy because of how many species there are.
Yeah, it can be very difficult to try to plot across a bunch of categorical variables. And we're not going to get into it today, but next week we'll talk a little bit more about how we can break apart graphs across different categories. But I love the box plot thing, and that is a nice foray into the next thing that we're going to talk about, which is box plots. So we can use box plots to visualize spread, and they tell us not just where the center is, but how wide data are distributed across some continuous variable within a category. So box plots are also geometric mappings that we would use aesthetically in our ggplot. But rather than a point, we would use a box plot. So we will add surveys complete again for our data set. And we can add a geom box plot. And when we do this, you can see it has all this information for stuff that we should add. But at the end of the day, what we're really interested in is the aesthetic mapping and the variables that we actually want to map. So we could say X equals species ID and Y equals weight. And let's see what happens when we run this. Well, that looks a little bit more meaningful. It's still kind of cramped because of the plotting window that I'm using. Now it looks a little bit better. And we can see where like some crazy outliers occur. We can see where data are really closely clustered. And something that a lot of people like to do is actually to add points over or under box plots so they can simultaneously look at sort of a summary of the spread and the raw data itself. So we can once again combine different layers, like I showed you with the statistical smoothing above, but rather than adding like some sort of trend line, we could overlay boxes with points. So once again, we'll add our data. And then we can also add our box plot. And we can also add points, but rather than using the geom point, which will exactly map a value to a value, we're going to use the geom jitter. And I really like to use the geom jitter with some of my work because it actually applies some spreading to your points. So they no longer fall on their true value. It's more to give an idea of where there are clusters of points. And I completely forgot to add my aesthetic mapping, so I'm going to do that. And let's look at what we get from this. Well, that's a mess. That's impossible to look at, right? We painted a bunch of black points over some black boxes. It would be much easier if we took this, but also added our alpha parameter, which is that transparency. And let's take a peek at that. Okay, now we're getting somewhere. But you can see we have some really dense points and some really, really barely even there points. Let's see. Oh, one thing I didn't talk about was color. We can also add color to plots. And I showed you how to do that aesthetically. That is, you are mapping a variable to a color, but you can also blanket apply color across all of your points or boxes or whatever you're interested in. So let's say color equals, what's a good color? How about cornflower blue? That's very pretty. There's about 1 billion colors that are available to you in R. And I'm going to try to show you. Okay. If you simply Google R colors, I guarantee the first thing that comes up, it already recommends it for me because I look at this page all the time. There's a website that has a PDF called Colors in R. And there's a ton of creative names for them. They span from the different shades of gray that you have available to funky names for blue, to tomato red, to sand. And there's a effective use of color. We'll get to that next week. But for the time being, just be aware that there are a ton of colors that you have at your disposal.
I just want to mention for any Wes Anderson fans out there, there's color palettes for each of the Wes Anderson movies available. So I use those a lot.
Yeah, the Wes Anderson color palettes are awesome. Oh, it looks like we have a lot going on in the chat. Do I need to?
I was just posting that link because I use that PDF all the time as well.
Oh, thank you so much. Let's see. Okay, so we have all these geom jitters and they're pretty dense, so it's really hard to see our box plot. One last thing I'm going to show you here before we break out into our major challenge of the day is that you can reorder these different geometries that you use to change the order that they're actually added to your plot. And so here, rather than having our base plot with box plots and then points jittered over on top of that, now we have our base plot with points jittered and then a box plot added on top of those. So right now you can see all the boxes are kind of obscured by the points. If I change the order that we add them, we can now see the boxes are on top of the points. But we still have a little bit of a problem, right? The boxes are opaque. You can't see through them, and who knows if there's points underneath them. So we'll do one last one. Within the call for box plot, we will set the fill value, which is the color that's actually inside the boxes. And we're going to set that to transparent. And now when we run this, we will have empty boxes that you can see through, but will retain the outlines of them. And so you can see a lot more data all at one time. That was kind of a lot of material. So let's take a deep breath and just sit back and look at everything that we've done and ask any questions that we have before we start the challenge.
I have a question.
Yeah.
I was just playing around with it, but can you not also use alpha argument instead of this fill equals transparent? And like, why would you, when to use fill versus when to use alpha versus when to use color?
Oh, that's a great
Might
question.
be too advanced, but
So you could do this same thing that we did above, but rather than say fill equals transparent, say alpha equals 0. And that would set the fill to be completely transparent. And so this will end up giving us the same plot that we had above, except the points you see, we've lost all of the points that come with outliers on the box plot. And that's because anything that's not a line construct of the box, it thinks it's fill value. So here was with fill equals transparent, and here was with alpha equals 0. And then you can also, for some of these, actually set alpha as an aesthetic plotting parameter. So we could say ggplot of surveys complete and add a geom, let's say point with AES x equals weight y equals hind foot length. And look at that quick. And we could say, this is not probably a great reason to do this, but we could say alpha equals year. And we'll now see on the side, we have mapped the transparency to the year that the data were collected. And really, really faint points are old data, and really, really bold points are much newer. So there's a lot of plotting parameters that you can set uniformly across the whole plot if you're not within your aesthetic mapping call, or you can make them variable according to some column in your data set by defining them within this AES parameter or AES function. Does anybody have any questions about that?
This is kind of just a more general question. Why, it seems like you were saying earlier that it just doesn't really matter where you put the aesthetic function, but I imagine that one day it will. And I just want to anticipate that.
Yeah, that's also a great question. So let's say you want to, a good example for this would be that the smoothing linear, well, it wasn't linear, but the smoothing trend line that we included before. So let's say that we are interested in weight versus hind foot length, or hind foot length versus weight, I guess. And if we include the aesthetic mapping for that up in ggplot, we will see that we just get a blanket series of black points. We can also add a smooth function, and I'm going to define the method as a linear model so that it makes a straight line. And it is going to generate a line across all of the data. But let's say that we want to color our points by the species and only have a line for the full data set. Well, then if we included color up here, we would end up with a case where all of the data for all of these geoms are grouped based on what our aesthetic mapping was above. Wow. So that's a real mess to look at, but it illustrates a point that I want to get across. Whereas instead, if we had defined the aesthetic mapping for color just within the geom point, the linear fit would only include our X and Y up here, but the points would still be grouped by species ID. So you kind of have to sit back and think about what exactly you want to be assigning variables to for the different geometries that you're adding to your plot. And I didn't see who asked that question, but did that sort of get at what you were asking about?
That was me. And could you just summarize that and say that again? Because I don't think I quite got it.
Yeah, so if you define aesthetic mapping within the ggplot function itself, it will apply that mapping to every layer that you add to your plot. But if you only want to map that variable for some element of, or for a single layer of your plot, that is just the points, then you would want to define the aesthetic mapping within that layer.
Okay. So you can do the aesthetic mapping function in multiple layers, multiple times.
Yeah, so I could even copy this and put it in the stat smooth layer, and it will go back to that original apply the mapping to everything.
Mhm.
And so now we have individual lines that are individual colors for each of our species ID.
Okay, that makes a lot more sense. Thank you.
Mm-hmm. Are there other questions on that? I know that ggplot is a lot to take in a 1 hour lesson. Okay. Well then, in the interest of time, let us begin on a series of challenges. So there are 3 sub-challenges here, and it's going to take you some time to work through this. I'm going to paste it into the chat quick, I think, if it lets me. And okay, there we go. I would like each of you to work for, let's take 8 minutes individually, because there's a lot going on here. And then work with your groups. We'll stick you in some breakout rooms for 5 minutes. And then we'll take the last 2 minutes of class to reconvene and see what we all came up with. Nick, do you want to send them to some breakout rooms then for a couple minutes?
Sounds good.
Okay, so just real quick here in the last 5 minutes of class, folks, do we have everybody back? It looks like approximately yes.
Yeah, everybody's back.
The first question asks you to, rather than use a box plot to look at your data, use a violin plot. So did anyone come up with a good solution for that?
Just instead of doing box, just doing violin at the end of what we were doing above.
Okay.
Sorry, GM point.
And so if we do that, we end up with this. Am I still sharing my screen? Okay. I lost my yellow box. Yeah, so now we have some weird looking violin inspired shapes. And does anybody have a guess for what we're actually looking at with the geom violin? Okay, I have the answer, so that's okay. These are basically density plots. So you can make a histogram. Geom violin is essentially that, but mirrored in two directions. So if you have some bimodal distribution of data, you'll end up with sort of a violin shape where it goes out and then pinches in and then comes back out again. And this can be nice because it sort of gives you a different angle at the shape and density of points within a data set. The one thing that we'll note here is that there's some really high values in weight, maybe not anomalously high, but there's clearly a lot more values that are close to 0 than there are close to 300. So the second part of the challenge asks you to look into scale_y_log10. Did anybody meet with success in adding the log 10 scale? I see at least one thumbs up. Megan, do you want to tell us what you did?
Sure. Yeah, let me just get back to my screen. So I did that, but then the plus after the geom violin, and then scale_y_log10.
Scale y log 10. And so what did this do? It converted our y-axis into a log scale. Now it didn't take the log of weight, but it changed the spread of the tick marks on the y-axis. So between the first and second tick mark, it looks like we tripled the change. And then between the second and third, it's approximately triple the change. And then between the third and fourth, we've tripled it. And this is a lot nicer to look at. And we can start to see some of these really funky areas where there's concentrations of weight within a species. And so maybe there's something going on with this PF species where there's like a ton of points right around 7, and then no points really between 7 and 8, et cetera, et cetera, et cetera. So the last part of the challenge asked you to subset the data for just 2 particular species, and then overlay a jitter plot on the hindfoot lengths of each species with a box plot. So I'm going to walk us through this quick for the sake of time. One really nice thing about how ggplot is set up is the first argument is the data set. So we can actually, at the end of the day, pipe data sets into ggplot. So first we will pipe into a filter where species ID equals NL or species ID equals PF. And then we can pipe the product of that directly into our ggplot. And we can add our geom jitter and our geom, what did we want? Box plot, right? And did I add that in the wrong order? Yes, I did. And let's add an alpha parameter just for some nice viewing. And we can see there's a really tight spread of weight for this PF and a much broader spread for weight in whatever the NL species is. Then it asks us to set the color according to the plot. So we will say geom jitter and add an aesthetic mapping just within the jitter. So this gets to what Kirsten was asking about. And we can say color equals, is it plot ID? But once again, we see this weird continuous scale. And so we can convert that into a factor. And now we have a nice series of breaks across our plot IDs. Of course, there's a bajillion of them, so it doesn't look very beautiful, but you get the idea. So that is a very brief introduction to ggplot. Homework 6 is posted. I know we went a minute over. Sorry about that, everybody. Thank you for those of you who stuck around. And with that, I think we'll call class a day. Have a great week, and we'll see you at seminar on Thursday.